Well, with tornado formation or tornadogenesis, what we're finding and what other people are finding is that you might have a rotational lock, but it's a rather weak rotation. And what's the characteristics of the surface are the important elements that trigger tornadogenesis. That could be topography, that could be variations in surface roughness, or it could just be surface roughness itself. And what we're finding is that circulation, weak circulation might be a lock, but what happens is the formation of a tornado occurs down in the lower several hundred meters of the atmosphere and then builds upwards. So according to that research, tornadoes don't really touch down and lift off. A better terminology would be tornadoes form down at low levels and dissipate at low levels.
Ben Franklin began the study of lightning 260 years ago, but to this day, scientists still don't fully understand how it forms. Sure, the basics are known. It's like a zap of static electricity, except on a much, much larger scale. In stormy updrafts, raindrops and ice particles rub together. Some become positive and others become negative. Then they're pushed apart by wind within the storm cloud. As a result, the cloud ends up with areas of different charge. Lightning is the spark that jumps between these areas. These sparks can also fly between the negative areas of the storm cloud and the positive areas on the ground, say through a tree or a golf club. Simple, right? But there's a problem. The electric fields measured in the thunderstorm clouds typically aren't big enough to trigger a spark. So what sets it off? Maybe cosmic rays. The idea goes like this. Cosmic rays, which constantly bombard the Earth, produce fast-moving, highly energetic electrons. These electrons collide with air molecules, which produce more speeding electrons, and so on. This process is called runaway breakdown and leads to an avalanche of energetic electrons through the air. These electrons forge a conductive path in the air, which triggers the discharge of lightning. Of course, the theory hasn't been proved, and there are other ideas for sparking mechanisms as well. It will take more work to fully solve the puzzle of how lightning forms. In any case, remember, the next time you get zapped pulling on a wool sweater, it just means you momentarily caught a little bolt of lightning. For Scientific American's Instant Egghead, I'm Philip Yam.
The Incredible Hulk was created by gamma rays.
Then an accidental overdose of gamma radiation alters his body chemistry.
The gamma rays that caused the Incredible Hulk were actually low energy compared to the ones that we're interested in. As soon as that crate arrived, we knew that we were beginning an intense few months of integrating all the different subsystems before shipping it to the telescope.
It is a global project. We now are almost 2,000 people working on this project.
Okay, here we go.
Together with the team, we're trying to make it work, and we're running into problems all over the place because no one's done this, so no one knows what's best.
Problems just come up all the time. There's always something to troubleshoot, and it's become kind of a hobby to deal with those things.
Yeah, look, this is easily the fastest I've ever assembled one.
What we're doing with the Trenkov telescope array is viewing light that's 1 trillion times more energetic than we can see with our eyes. These trillion electron volt gamma rays, each one of them collides with the atmosphere, and it basically shatters a molecule of air. Now, some of those particles can emit a flash of blue light called Cherenkov radiation. And so what our camera does is that it collects that flash of Cherenkov light, and together you make this movie at 1 billion frames per second of the air shower, the air cascade of particles developing in the atmosphere.
And the technology, the photon detector technology that we're using here, they have to be very fast, and we need to be able to identify individual single photons that hit the surface.
So I think I get a nice pulse now this time.
And by measuring these gamma rays, measuring their intensity as a function of energy, their characteristics as a function of time, we learn about the acceleration processes of the charged cosmic rays inside the sources.
And through this instrument, we can view some of the most extreme and fascinating objects in the universe. We might also be able to detect dark matter. We know that it makes up most of the matter in the universe, and yet we basically have no idea what it is. And so if we could detect dark matter particles colliding with one another, converting into very high energy photons, then we could confirm the idea that dark matter is made of particles. And that would push the field forward in terms of understanding what this kind of shadow matter throughout the universe is actually made of. I got excited about astroparticle physics when I was actually in college as an undergrad, much like the students who are in the lab here today.
It makes me happy to know that I'm part of such a big collaboration that's striving towards the future, that's striving towards knowledge.
When it comes together, you realize, oh wow, so many people have put so much time into this, and here it all is. You know, it's working.
The story of the integration here at the University of Wisconsin will come to an end, but that'll start a new chapter, which is getting everything to work on the telescope. I'm sure the first time we turn it on, we'll see some surprises. We'll need to do some more work and get everything tuned correctly. But I'm confident that once we do that, we'll be able to detect these air showers and start doing science with them.
The cosmos is a vast and intricate web of cosmic phenomena, each emitting various forms of electromagnetic radiation. In the quest to understand the universe, astronomers employ an array of observatories and instruments, each tailored to capture different aspects of the cosmos. LOFAR, the low-frequency array, is one such revolutionary instrument designed to explore the universe's radio sky in unprecedented detail. LOFAR represents a remarkable collaborative effort between European institutions and has opened up new avenues for scientific discovery through its groundbreaking low-frequency radio observations. The concept of LOFAR began to take shape in the early 2000s when astronomers recognized the need for a radio telescope capable of observing the universe at exceptionally low frequencies. Traditional radio telescopes were constrained by their design and operational frequencies, limiting their ability to probe certain cosmic phenomena. LOFAR emerged as a solution to these limitations. LOFAR was developed by Astron, Netherlands Institute for Radio Astronomy, in collaboration with an extensive network of European partners, including universities and research institutions. The project received support from the European Union, demonstrating the significance of international collaboration in advancing scientific research. What sets LOFAR apart from conventional radio telescopes is its innovative design and cutting-edge technology. At its core, LOFAR is an array of thousands of individual antennas spread across multiple European countries. These antennas collectively function as a single, massive radio telescope. The array's antennas are grouped into stations, each containing several antenna tiles, which are further divided into so-called low-band and high-band tiles, allowing LOFAR to operate at a wide range of frequencies. Key components of LOFAR's technology include 1. Low-frequency operation. LOFAR specializes in observing the universe at low radio frequencies, ranging from 10 MHz to 250 MHz. This frequency range is particularly valuable for studying phenomena like cosmic dawn, radio galaxies, and pulsars, which emit radiation at these low frequencies. 2. Phased array technology. LOFAR employs phased array technology, enabling the electronic steering of its primary beam without the need for mechanical movement. This technology provides rapid scanning and tracking capabilities, crucial for capturing transient events in the radio sky. 3. Central processing. Data from all LOFAR stations are transported via high-speed fiber optic links to a central processing facility in the Netherlands. There, powerful computing clusters process and correlate the data, creating high-resolution radio images. 4. International array. LOFAR stations are distributed across several European countries, with the core in the Netherlands and remote stations in Germany, France, the United Kingdom, Sweden, and other nations. This international array configuration significantly enhances LOFAR's sensitivity and coverage.
Everything in the universe sends out radio waves: planets, nebulas, comets, pulsars. These radio waves, which are invisible to the eye, are sent out in every direction and can travel billions of light years to eventually reach Earth, although the signal has weakened quite a bit by then. Here they can be detected by radio telescopes, such as the International LOFAR telescope, which spans several countries. Each LOFAR station consists of many antennas. These different antennas catch the radio waves and send them to a central receiver, which converts the analog radio waves into a digital signal. This is done at each separate LOFAR station and in each participating country. Subsequently, all the digitized signals come together at a correlator, Cobalt, in Groningen, which is a powerful supercomputer. In turn, Cobalt processes the received data. However, there is also the issue of the data being polluted. It needs to be cleaned first. So let's go back a bit. The radio waves that reach our planet are distorted when they pass through the Earth's ionosphere. This distortion is comparable to how a diver, looking from underwater at a person standing at the edge of a pool, sees that person. The rippling water surface distorts the image that the diver sees. but the diver knows that he is looking at a distorted image and the actual person looks different. But we have developed algorithms for LOFAR to correct these distortions. Another form of pollution is radio signals sent out by devices such as mobile phones and drones. These radio waves come from other directions and are much stronger than the radio waves coming from the universe. These pollution radio waves are filtered out. The data arrive at the correlator Cobalt, which processes these data in real time and sends them to a SEP cluster. Here, the data are filtered, corrected, and processed further offline. Finally, these processed data are archived, and users, astronomers, can retrieve the data for further processing to, among other things, create an image.
Hi, I'm Brian Hare. I'm a researcher at Astron, the Netherlands Institute for Radio Astronomy. We are here at the LOFAR radio telescope, which I use to study lightning. Here we have a small spark generator called a Wimshurst. If I turn this crank, it will make sparks in between these two metal balls. And then over here we have a radio. If I turn it on, it'll make a little bit of static noise. And it'll actually pick up the radio waves that are being made by the sparks. This is very similar to like LOFAR, which is like a radio, but much more fancy and sophisticated, picking up radio waves being made by lightning. So now if I turn this, you can hear the static sound from the radio becoming quite a bit louder. Small sparks are like small lightning flashes. They emit lots of radio waves, which we can hear with the radio. So this is a bit of a demonstration about how LOFAR can also pick up and listen to the radio waves coming from actual lightning above LOFAR. We can use this data to image and map lightning as it gets started and grows through a thunderstorm, and even as it connects to tall structures like wind turbines and tall buildings. We do this because we really don't actually understand lightning. We don't understand how it gets started, we don't understand how it grows, or why it does any of the other weird stuff that it does. So by making images in this way with LOFAR, we can try to probe the plasma of the lightning to understand how it's working.